Hey dudes, Did the Builder here, and in this episode of Zig in Depth, we're going to be looking at Zig's C interoperability features. And these features of Zig make it stand apart from most other languages, in that usually in other languages, when you want to interoperate with C, you have to use some type of foreign function interface, FFI as it's known, or you have to generate some bindings and use some special tooling. But in Zig, the integration is totally seamless. It's almost as if your Zig code and the C code are basically at the same level. And we're going to be taking a look at a simple example of a little C program here. We're going to start out with the situation in which you can use the Zig compiler as a C compiler, okay? So here we have a little C header. It's called math.h. And in normal C tradition, in a header file, we're going to have the definition of function signatures and any necessary macros that we were going to be using in our C program. So here we have the header, header guard as it's known. So this avoids multiple importing of this header file. This is traditional in C headers. Here we have a signature for a little add function. It takes a couple of ints and returns an int. Here we are conditionally defining a macro here called increment by, and we're setting its value to 1. So if in the environment where we're going to be executing this macro is already defined, then this condition here will be false. Okay, this basically says if it's not defined, then we define it. Okay, and here we have another function signature called increment here, the function. It returns an int and it takes an int, and it'll basically be incrementing that integer. And finally we have the endif for the header guard. Okay, now here we have the implementation file, which would be math.c. First of all, we are including our header file, the one that we just saw. Here we have the actual implementation of the add function, which basically just returns a plus b. And here we have the implementation of the increment function, which basically just adds the value of the increment by macro to whatever is passed in as x. Okay. Here we have the actual main.c program file, and here we're going to be including stud.io because we're going to be printing to the screen. We are including here our header math.h, so we can have access to those functions. And in our main function, we are defining here two variables, a and b. We're calling here our function add and assigning the result to c. And here we're going to be printing out that result. And also here we are calling the increment function and passing it a. Okay. And finally we return 0. Okay. So it's very simple, little C program making use of a tiny little library, which would be this file, and that library has its header, which is this file. Okay, so that's basically the structure of what we're going to be working with. If I have these files I put them in the same src directory as we have our main.zig. But for now, main.zig here isn't relevant. We're only going to be making use of the C code because we're going to be compiling the C code as you would with any other compiler, but we're going to be using Zig. So let's try that. We basically use Zig CC, and we have to list out the files that are going to be necessary to compile this program. So we're going to need math.c, okay, and we need to compile also main.c, and we can tell it that we want to output this as let's call it math. That's going to be the name of the binary executable. And that was fast. let's take a look here at our directory listing, and as you can see, we have here a binary called math. Okay, if I take a look at what type of file that is, it says it's a Mac-O 64-bit executable, AARC64, because I'm on a Mac M1. And let's run that executable, and there you go, there's the output. So you can see how we can easily, with the Zig toolchain, compile a C program. No Zig code here involved whatsoever. We're just using Zig as a compiler for our C code. And this is a really powerful feature of Zig, because usually having a whole C compiler toolchain can be quite a complex installation and configuration operation that you have to do in different operating systems. But as you saw with Zig, all you have to do is just download one single file, extract it, and basically that's it. You have everything you need in that Zig command. Okay. And another really powerful aspect of this, let's remove this executable, and now let's go back to our compile command, and if we do this, target x86 64 -linux -gnu, and that was fast. Now let's look at the files. As you can see, there it is. Let's clear the screen, and let's look at what type of file that file actually is. And now it says that it's an ELF 64-bit LSB executable, x86-64. So with just adding that target here option to the Zig compiler in its C compiler mode, we have just cross-compiled this program on a Mac M1 to an x86-64 Linux GNU executable. Okay, and this also is a pretty big deal, because usually when you want to cross-compile C programs using other tool chains, it also requires a lot of setup and a lot of tedious configuration of the tool chain. And as you can see, with just the Zig executable, we can also do easy cross-compilation of C programs. Okay, so that's a really impressive feature of Zig. Now let's see how we can compile this C program using the Zig build system. Okay, so I have here my build.zig, and as you can see, we have here the exe definition here of this constant, calling the add executable method of the builder. We're going to be talking in a further episode exclusively about the build system, but for now, this is basically the executable part that's always included in the default build.zig that's generated when you do zig init exe. All I did here is that now, instead of pointing to main.zig, I'm pointing to main.c here. Okay, and here I'm making this call to add C source files, and here you give it two lists, two slices basically of strings. The first one is going to be the strings. Each string is going to be a path to a C file that you're going to be needing. Here, to compile main.c, I'm going to be needing to also compile math.c, because it contains the functions that I need, right? And the second slice of strings, which in this case is empty, is a set of flags that you can pass to the compiler for each one of these files that you're going to be compiling. Okay, and also here we're also indicating that when we're going to be compiling this, we're going to be setting an include path, which is going to be src also, or src directory. And what this does is, whenever we encounter an include for a header, the compiler is going to look in this directory, src, okay? And that's where we have our math.h, which is going to be needed by math.c, okay? So with this build.zig file, we can go here to the command line and do a zig build run. And as you can see, we have the same output. And I specifically added this C here, C prefix, so we can be sure that this output is being generated by this main.c file and not our zig file, okay? And if we take a look here, let's look inside zig out bin. And there we go. We have this 49K executable. Once again, the convention for building is it'll give it the executable the same name as a project name. This is also found here in the build.zig. Here is the name. Okay, if you change the name here, it'll give it another name, the executable. So now you've seen how you can compile directly by using the zig cc command line compiler, or you can use the build system to compile your C project. Here we are exclusively compiling C. We're not dealing with zig code at all, okay? But if you do want to integrate C into your zig code, let's take a look at that. I have a file here. This is a main.zig. And there are a couple of ways of doing this. The first one I'm going to be showing is using the @c_import built-in, okay? @c_import basically is a built-in that lets you integrate your C code into Zig, okay? And here what we're doing is we're using the @c_define built-in, which lets you define macros, just like you can define macros in C. You can define them here with this built-in. And what we're going to do, we're going to setting that increment by macro. Let's take a look once again here at the header. Increment by, if it isn't defined, it's going to be 1, okay? But here we're going to be setting it to 10, okay, by using this @c_define. There's also an @c_undef, which lets you undefine macros. And here we're using this built-in @c_include, which lets us include directly in our zig code a C file. Okay, so here we're including this math.c, which contains those functions that we're going to be using. And all of this, the result from all of this C import, we're assigning to this constant called math. Okay, so this basically also lets us namespace these functions that are coming from the C world. Okay. And here in our main, what we're going to be doing is precisely, we define once again our A and B variables. And here we're calling within this math namespace that we created, the add function, passing it A and B and assigning the result to C. And here we're going to be printing out with the zig prefix to make sure that we are executing that zig code. And the result of that add, and here once again we're calling increment in that math namespace. Okay, we have a lot of things here commented out because that's to demonstrate the other way of doing things. You can ignore that for now. Okay, and let's go over to our build.zig. We're going to have to make some changes here because now we want to be compiling our zig code. So let's change this to main.zig. Now we are not going to need this, okay? We will need the include path because we will be importing when we do this include here of math.c. Zig needs to know where that math.h file is. So that's why we still need here to specify the include path, which is going to be src, and it'll be able to find that math.h file. Okay. So with that, let's save the change here to build.zig, and let's make sure that all changes are saved here. And now let's clear the screen And let's compile, build, and run. And here we go. We have the Zig version now of the program, of the project that was built. And we have also, as you can see, the increment here, instead of just being 22, now it's 31. So in effect, this definition is kicking in, okay? If I comment this out, let's run this again. Now you see that we have 22 instead of 31. So as you can see, the integration with C in Zig is really transparent, really seamless. We're basically importing directly here the Zig code, the C code, sorry, into our Zig code, and we can make use of that library of those functions in our Zig code, calling it here basically directly, okay? So the other way I wanted to demonstrate is that since that C code that we're using is basically a library, we can compile it as a library, a static library, and then use it that way, okay? So let's go over to our build.zig, and the first thing that we have to do is take a look at how do we compile that C code as a static library, and we do this with this block here. Let's uncomment this. As you can see, we're defining here a lib constant, and it's the result of this method, add static library. And once again, we give it a name, and we tell it which is the root source file, which is going to be that math.c file, okay? And then what we're going to do is, if for example we want to use that library in another project, we can make this call here to install the artifact. This will create the actual file for the library and put it in the zig out directory. We're going to take a look at that in a little while. We're not going to be using it for now. And here in the executable, what we have to do is we can now comment this out also. We're really not going to need that. And we want to link that library, okay? So we have that lib constant, which is going to reference that build of that static library that we are defining all the way up here, okay? And here, what we're doing is, when we want to build this executable, our Zig executable, we're telling it that we want to link that library that we just built, okay, which is the C library. So let's save this. Now let's go to our main.zig file, and we have to make some changes here. Now we're not going to be importing directly that C code. What we're going to be doing is we're going to be accessing those functions as extern functions from a library, okay? So we use the extern keyword here, and we define the signatures now using Zig types. We have add and we have increment, okay? And now we comment out this one, and we uncomment here, because we are not using the math namespace anymore. We have access directly to that function, add. And here we're going to comment this and comment this one to have access directly to the increment function, okay? So let's make sure that we have everything saved, and let's clear the screen here, and let's give it a try. Now if we once again do a directory listing of zig out, we only have the bin folder because we're only telling it to generate the binary artifact, okay? Let's go back to our build.zig, and we have this line, where is it? Here, install artifact lib. We uncomment that. Let's clear the screen. Let's build once more. Okay. Now, if we look at zig out, we see that we have indeed that lib folder now, okay? And if we look inside that lib folder, we have libmath.a, okay, which is the convention in Unix-like systems, when we have a static library, it'll have the .a extension, and it'll add the lib prefix to the library name. Since we said that the library is called math, it calls it libmath. So as you can see, this is yet another way that we can make use of RC code inside of Zig. Basically the traditional method of compiling a static library. It can also be a shared library also. And then by means of the extern mechanism, as we can see here, we can make use of that library. One extra and final little detail I wanted to demonstrate in this video about Zig C interoperability is that we do have access to the C standard library functions directly in the Zig standard library in the stud.c namespace. So here, as you can see, this is that last print that we're seeing here in the output right here. This last print is actually being done by the printf function from the C standard library, and that's available in the stud.c namespace. Okay, so we're making here use of that printf. This is not the debug print from Zig. This is the printf from the C standard library. And also in this case, we didn't make use of linking the C standard library in our project because our example didn't make use here. Our little library didn't make use in any area of the standard library. It was just pure C code. But if you're using a library that does require the C standard library to be linked in, which is very common, you can do that by adding exe.link libc. Okay, here, this function. If you add this to your executable, you will link the C standard library to the executable. Okay, and with that, that's basically everything I wanted to demonstrate about the seamless C integration in Zig. There's a lot more that has to be covered when it comes to types and how to handle data types between Zig and C. Maybe in a future video we can touch upon that. But for now, I just wanted to demonstrate how you can integrate the C code directly into Zig and also use Zig as a C compiler. Okay, so hope you find this useful. Do the builder here. I'll see you in the next one.